Hey guys, in today's video we'll be going over the TCP/IP stack model. So what is the TCP/IP stack? The TCP/IP stack is another name for the Internet Protocol Suite, which is a conceptual model that represents the set of communications protocol used in the Internet and within similar computer networks. It is commonly known as TCP/IP because the foundational protocols of the suite are the Transmission Control Protocol and the Internet Protocol. But why is this model important? Well, when we send information across a network, including the Internet, that information must be packaged into a format that allows the networking device to read its source and destination address along the way. This device is known as a router, and it helps to direct traffic on the Internet. When we send out information over a network, we call it a packet, with the data inside of it being formatted in a special pattern that routers can recognize. This formatting is in the form of a header, a piece of data that's attached to the front of some data that we want to send over the Internet. Anytime we send a packet over a network, it's wrapped or encapsulated in several layers. From outermost layer to in, these are data link, network/internet, transport, and application. A neat mnemonic to remember these layers is do not throw away, as in do not throw away your notes on this topic, since understanding these layers is really important. The basic reason for having multiple layers is much the same as the reason you'd use different kinds of packing material when shipping something through the mail. Say you have an antique vase worth several $1,000s and you need to ship it across the country. The vase is your core data, the thing being sent, the reason for all the packaging. It's like the application layer. Because the vase is fragile, you would want to wrap it in bubble wrap or maybe even include foam peanuts. This is like the transport layer. The Postal Service needs to know where the box is going and where it's coming from, and this information could be on an address label. This is like the network/internet layer. Finally, the vase and all its packing materials have to be wrapped in a box. This is like the data link layer. The only difference between our vase package and our digital packet is that whenever your packet reaches a new router on its journey, that router has to open up or decapsulate the packet. For example, it needs to remove the data link layer so that it can read the information inside the network/internet layer. It then adds data link headers to the packet again and sends it on its way. Now that we understand the stack as a whole, let's look at the stack more in depth. Let's say we want to access a web page. When you do so, your server sends a message to the web server using HTTP, the Hypertext Transfer Protocol. HTTP is a sort of language that clients and servers can use to communicate with each other and to send content back and forth. HTTP communication is at the application layer. This is the core of a message sent over a network. Headers will be added to it in several layers to ensure that it's transmitted correctly. To access the contents of a website, your computer sends an HTTP GET request. If the server has a web page the client is asking for, it sends back a status code of 200 OK, along with the content of the web page. If the server doesn't have the page the client is requesting, it can respond with a code of 404 not found. After sending the GET request, your packet reaches the transport layer. There are two main kinds of transport layer headers, TCP and UDP. Remember that TCP stands for Transmission Control Protocol. UDP stands for User Datagram Protocol. TCP traffic is slower but more reliable, while UDP traffic is faster but less reliable. This is because there are three messages transmitted by TCP, known as the three-way handshake of SYN, SYNAC, and ACK. This mechanism is designed so that two computers attempting to communicate can negotiate the parameters of the network TCP connection before transmitting data. Think back to our vase example. Since our vase is fragile, we pay for extra bubble wrap and foam peanuts to keep our package secure. Although it would take more time to do so, securing our package is more important to ensure that it reaches its destination securely and safely. However, if we were sending only a letter, we wouldn't need such safeguards, and instead we focus on how fast our message can be received. Such is the difference between TCP and UDP respectively. Back to our web page scenario. HTTP traffic uses TCP, so we'd wrap our HTTP GET message in a TCP header. IP source and destination addresses are stored in the Internet/network layered header. The Internet Protocol or IP header is wrapped around the packet after the transport layer header is attached. Note that this process of adding multiple layers of headers is called encapsulation. To follow along with our web page example, our network layer IP header for this packet would have our computer's IP address as a source address and the web service IP address as the destination address. But how do we know what physical device owns the IP address of your computer or of your router? Well, this is where physical addresses, or MAC addresses, come in. Every network device has a unique MAC address. When we send a packet over a network connection, whether it is wireless or wired, we need to address that packet to the MAC address of our default gateway, which is our router. The source and destination MAC addresses for a packet are stored in the data link layer header for traffic. When we're using a wired connection, the specific name for this header format is Ethernet. So just like we use TCP or UDP at the transport layer and IP at the internet layer, we use Ethernet at the link layer. Every time we transmit a packet across the network, we need to rewrite the source and destination MAC addresses because the packet will be transiting between new physical devices. And those are all of our layers. I hope this video helped you to understand the TCP/IP stack and its importance in networking.